So Amanda, please.
Hello, everybody. Thank you very much. Can you hear me well?
Yes.
I guess so. Okay, so this is, well, as I just told Mel, I'm in China, 12 hours apart from the people who is in New York or in this franc in the hour. So but I'm in China with Mexico jet lag. So it's a complete mess. Let's see how it works. Anyway, I'm very excited to present this work. This is a work that I really like a lot. I really enjoyed to work on this. Also, once Mel mentioned, this is my father, Luis Montejano, and Uriel Serra. We are both from Mexico, Universidad Nacional Autónoma de México, and Uriel Serra is my academic father. So he was my advisor when I did my PhD many years ago. So this is a work that it means a lot to me. And also it's about a problem that somehow relate our different interested. So we put powers and energy and different abilities together, and I think we are obtaining nice results. So to start with, so the title is Discrete Brunn-Minkowski Inequalities. I will present several results, but I will focus only on one. And most of focus on the result, I want to focus on the techniques that we developed. And in order to start, let me see how this works. Oh, yes, perfect. Well, I have to recall what is Brunn-Minkowski inequality. This is a very classical result in convex geometry, but also it touches several areas in mathematics, and I think it's beautiful. It's about compact sets in an Euclidean d-dimensional space, and it is an inequality that relates the Lebesgue measure of the sets of two sets, let's say A and B, and it's a Minkowski sum. The Minkowski sum is defined here, and it is actually, so all this is in the continuous world. So I have a picture here. Just for example, in R2, we can have this set, like all full set, or all points inside the shape, and Minkowski sum behaves like this. And in this case, the measure is just the area of the figure. And anyway, this inequality is known to be tight, and equality holds only if and only if A and B are homothetic convex sets. So there are many things to say in this area, but when we turn our attention of what would a discrete Brunn-Minkowski inequality look like, then we enter in the combinatorial additive number theory world, as we are going to see in a moment. So the first time I prepare this, I give this talk, I present these results. I spent quite a lot of, well, I spent some of the time in the talk in order to give a context, to give the to explain why this is an interesting problem and how it's related with and other results in the literature. But since today I only have 25 minutes, now less, I will skip this part. Anyway, I leave the slides and I will pass it very quickly, just because they are there. And so also you can see very like a overview where how this is related with other results. And then if you find something interesting there, you can ask me. So I will skip this very quickly. This is related, of course, with a very recent breakout on the problem by Peter Van Hinton, Peter Kivash, and Michael and Marcus Tiba, but I will not go into this part. And so there are, this is related, the work of thinking of discrete Brunn-Minkowski inequalities has been touched with several authors, and the only thing I want to emphasize is that in the in the continuous world there is a straightening of the Brunn-Minkowski inequality by Bonnesen. This is also from the past century, beginning middles of the past century. And again, I will not explain precisely what is this result. But what I wanted to say is that somehow the recent breakthrough of the solution of confirmation of Russia's conjecture, it can be seen as the discrete analog of the right formulation in some sense, but the Bonnesen, which is inequality, which is straightening and has a different perspective, it has also a discrete analog only for dimension 2 in the discrete world. Anyway, I will explain this in a moment, but I wanted just to mention this as a context. The result is here, but for now, I don't want to read it. We are going to get into this in some minutes. So I wanted to go directly to the main problem that we are interested in, and after, if I'm able to explain this properly, after maybe you can get why this is an appropriate, a good way to try to obtain discrete inequalities, which are analog to Brunn-Minkowski inequality. So for the discrete world, we are going to still work in these Euclidean spaces of dimension D, but we can also consider any different groups here. But for today, I will be stay in RD. And let me just define one function, which is this orthogonal projection. When we consider an orthogonal ordered base of our space. And it is important that our base is ordered in order to know which projection is P1, P2, P3, up to PD. For example, if we are in 2 dimensions, we only have one orthogonal projection, which is P1, And this is depicted here. And I mean, maybe I can put the problem in order to understand. Our problem is to understand or to find sufficient conditions for this inequality to be true. And so let's try to slowly analyze what this inequality sets. So this is a lower bound. Our sets in RD are going to be finite sets. Now we are thinking as we think in combinatorial number theory in finite sets. And the measure is going to be the cardinality of the set. And we want to say something about the cardinality of the sum set in terms of the structure of the set sum sets, the original sets A and B. And if you look here, we have some expression relating the cardinality of these projections. And these cardinalities, what really are the number of hyperplanes of lines or hyperplanes or k-dimensional hyperplanes, the number of parallel of these hyperplanes that intersect my set. For example, let's go slowly. Let's see what this inequality sets, for instance, for one dimension. For one dimension, if you we observe that here we have a product of d factors. D is the dimension. So for one dimension, we are going to obtain just a lower bound with one factor. For 2 dimensions, we are going to obtain a lower bound, which is a product of 2 factors, and so on. So for 1 dimension, if we have to make the conventions that P0 is 1, so this cardinality is going to be 1. P1 is going to be the whole cardinality of the set A, and so we will obtain this folklore inequality for finite sets in the real line, which we know that it's tight only for arithmetic progressions if the sets are large enough. And let me go more quickly. For 2 dimensions, we obtain a 2-factor inequality. And if you make carefully the computation, here I put the 1. Well, you can compare this with the previous result from Grinkiewicz and Serra that I mentioned. And this is precisely the discrete analog of Bonnesen inequality, which is it's very from my point of view, it's a very good way of understanding a discrete version of Brunn-Minkowski inequality. This result is only, I mean, this is a beautiful result from 2010, and it's only for dimension 2. So somehow we want to generalize this result, and one way of do it is thinking of this problem, this the product inequality that I put here. So let me put, I write here the bound for dimension 3, and I want you to notice that this is not true. That's why I put the problem. I didn't put, our project is to prove this inequality because we already knew this is known since many years ago. there are examples that does not fit, for which this inequality is not true. But for example, I have here an example. I don't have time to explain it carefully, but I guess that with the definition and this chain of here, if you want to take a picture and you get bored, you can verify these numbers, and then you can see that there is a. Remember that I told you that it was very important that the order, the base of the space, in this case, we are considering the canonical base. It is very important, the order. So what happens here is that with some order of the basis, I mean, this inequality gives different numbers if I project first to the xy plane and then to the x subspace, or if I do it in another order. The point is that there are ordered bases, even there is an order in the canonical base for which this inequality is not true. And here is a very small example. So what is coming back to our intention, to our purpose, what we want to do is to understand under what conditions or this inequality is true. And well, we have so far we have several results, but there are, I think, three results which are relevant in this direction. One is a generalization of the Grinkiewicz-Serra inequality for any dimension, but only with two products. Today I will not talk about these results, but I mention it because it is need to obtain the result that I want to present, which is the parameterized version. There is another very nice, well, there is another, consequence of our tools that is somehow the verification of the truth for this inequality in dimension D with the D products, which is what we hope, but in some special case where we can find one-dimensional subspace that is aligned in the space where both projections are the D-1 dimensional boxes, and this is related to something in the literature which is interesting, so I will not talk about this as well today. I think I only have like probably 6 minutes, so I will, as I told you, I will present you only the parameterized version of our theorem. But as I told you, I want to emphasize in the techniques, in the tools that we are going to use. First of all, we will use compression, which is already a classical or very useful technique used in this kind of problems. Second, we developed a theory of weighted sets, which is the main thing that I want to communicate. And then we work with some weighted matrices and use different kinds of arguments in order to obtain our theorem. So what is a weighting set? Let me give you the definition, And probably it's better to give an example here. For example, in two dimensions, a weighted set I mean, we are going to work again with finite sets. In this case, I'm thinking the sets not with integers entries, and also I'm thinking that the sets are compressed, so they have some control shape, but the sets are going to be weighted. So I will have a weight in each point of the set. And then I will define for the sum set of my sets, weighted sets A with this weight and B with this weight, I will define a new weight, which is the sum weight of the sum set. And this is going to be defined as the average of the weights. For anyway, the weight can be an integer. It has to be positive, but it can be a real number. It doesn't need to be integer. And so the measure, instead of the cardinality, is going to be this average value, and the way of assign the weight to the sum set is defined in this manner, which is the precise manner to connect the weighted sets theory to our problem. So I have here an example again, but I will not go into with detail. The only thing that I want to mention here, reaching the final of my talk, is that there is parameter which we call alpha, which is the key parameter or the clue in order to understand when we will have our D product inequality and when no. And this is by studying this parameter alpha defined as this radio. So we will it's somehow like a like how it says, well, it doesn't matter. So here is the definition. It is important for us to study this radio. And why is this? Because we have a basic lemma which give us the opportunity of started an induction machinery by doing orthogonal projections, one step by a step, and but at any moment we are going to have the parameter alpha. So if alpha is greater or equal to 1, this lemma will give us our theorem as we wanted. Or in other, here I think I have, let me explain this carefully. So in other words, the problem, in other words, we can say that the product inequality works if this radio, if the sets and the weights of the sets are in such that the alpha is greater or equal to 1. We want to understand this. And by studying that, we are able to prove, for instance, the boxes theorem that I mentioned here. As I told you, in general dimension, if we have two finite sets and the orthogonal projections are defined as in the first slide, so we will have the wanted inequality, which is the strongest one that we can aspire to, if we can find our first projection. With our first projection, we can find, the sets are d-1 dimensional boxes. This, for instance, recupera, so give us give us ay, ahora no puedo apagar esto. My timer is telling me that I have to stop, but I cannot. Anyway, this is my late slides. With this result, we have a new proof of the Grinkiewicz and Serra two-dimensional case, because in this case, we always have this situation. And the parameterized version, as I told you, we have it in general for alpha, for 3 dimensions is going to look like this. Sorry, there is one more slide. We were able to prove that this parameter is the best we can prove is that this is greater than 1/2. Remember that we want greater than 1 in the general case, but and also what we obtained here is tight, but anyway, we want to understand. So we have examples that attains this inequality with 1/2, but we want to understand, completely understand in which cases this alpha or this radio of the weighted cardinalities is greater than 1. And so I haven't time to talk about this local expansion property, which is related, but I think this is all I wanted to say today.
Thank you, Amanda. Any questions for our speaker? If not, we thank Amanda again. And
Thank you.
The talk will be in 3 or 4 minutes. Thank you, Amanda.
Thank you.
Isaac, are you there?
Yes, I am.
Excellent. Can you put up your slides?
Yes, I can.
Nice to know where it's the not the opposite. It's one that it works, but how can you get out of one? Or can you? But if there's any,
We'll start in about 2 minutes.
Sounds good. Thank you.
It's the nice little all things knowing that's in the space station wise higher in your talk, you called something a multi-set union. Oh yeah, multi-set sum. Right. Yeah. Okay. The multi-set union is the max of the multiple sets. Add max. I would say that why wouldn't they have it here? Because the people who do the multi-set stuff, they want regular set theory to be a special case. Right? So